Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin. Wassalamu ala sayyidina Muhammadin wa ala alihi washabbihi ajmain. Rabbi shrah li sadri wa yassir li amri wa uqdatan min lisani yafqahu qawli. Rabbi zidna ilma warzuqna fahma. Allahumma faqina fi ma ta'wil. Okay, assalamualaikum. Okay, alright. So welcome back to fluid mechanics class. Okay, today we will continue with chapter 2.4, which is buoyant force. Okay, in this chapter we'll be looking at Archimedes principle, buoyant force, buoyancy, stability of floating bodies. Okay. So first of all, let's look at what is Archimedes principle. Okay, Archimedes principle states that a body in a fluid, whether floating or submerged, is buoyed up by a force equal to the weight of the fluid displaced. So, for example, we have here tank. We have a tank here, and we have water inside the tank. Fill up the tank until to the top of the tank, and then if you put something in the tank, for example, you put a cube of rock, for example, put a cube of rock, and then we will see that the water will be poured out from the tank because we put something in the tank. The tank is already full. Okay, so if you collect the water that you collected, okay, we have for example volume V. Okay, the weight of the water that you collected, let's say we have W, is the same as the force. Force FB means that buoyant force from the water to the cube is equal to the weight of the water that has been displaced from the tank. Okay, that we have there. Okay, and then so what is buoyant force? Okay, buoyant force is the upward forces of fluid exerted on a body immersed in it. Okay, the buoyant force acting on the body is equal to the weight of the fluid displaced by the plate. Okay, for example, the example I had given it before. Okay, so how can we write? For example, we have here a plate. Have a plate here. So, for example, you have a plate. You have a plate, and then we have a tank. The tank is filled up with water. Okay, you put the plate inside the tank, and then the water will pour out from the tank. Okay, and then you collected the water that pour out from the tank, and you weigh it. Okay, the weight of the water displaced is the same with the force FB, buoyant force that exerted from the water to the plate. Okay, the same example as before. Okay, alright. So how you can write the FB? So FB is equal to. So we have here FB is buoyant forces. Okay, buoyant forces. We have here buoyant forces equal to the F bottom minus F top here. So for example here, you put a cube inside it, and then we have a force from the bottom of the water and the force from the upper surface of the water. Okay, so FB can be written as, for example, we have here F bottom, FBOT, F top, FTOP. So FB equal to F BOT minus F TOP. Okay, we can write as like that. Okay, or okay, we know that. Okay, so we also know that the force from the water F from the water is equal to rho G H, right? F rho G H. Rho G H. Okay. So here we have rho G H times A lah. A, YA, because F as we known equal to PC A. PC equal to rho G HC. This is what you learned before. Okay, so rho G, H times A, so we got FB. Okay, so we also know that if rho G, okay, H is actually height, A is area. So what you will get if you times height with area? So we have height and then we have area. We got volume lah kan? So we got volume. So we have here H and we have here A times H, we got volume. This actually. So we can write FB also equal to rho G V actually. Okay. Alright, so we can also write B is equal to rho G V. Okay, next what we're looking at. Okay, for floating bodies, the weight of entire bodies must be equal to the buoyant force, which is the weight of the fluid whose volume is equal to the volume of submerged portion of the floating bodies. Okay, now let's look at floating bodies. Okay, for example, we have here is the water surface of water in a lake, for example. And then you have floating bodies. For example, here we have a floating bodies. For example, here we have a ship looking like this. Okay, for example, ship looking at this. Okay. Okay, alright. So these are floating bodies. Okay, for floating bodies, the weight, it said before, the weight of the floating bodies is equal to the water displaced by the volume submerged in the water. Yeah. Alright, it said here that floating bodies, the weight of entire bodies, here is entire bodies, must be equal to the buoyant force, which is the weight of fluid whose volume is equal to the volume of submerged portion of floating bodies. Okay, alright. Okay, we have here, okay, the portion of the body that submerged is only here from the water surface to the below lah. Okay, so this is only the portion of the water, the volume that submerged. Okay, the volume submerged. V, I said VD by volume displaced. Okay, so the weight of the entire bodies, which is the weight of this, the pink color here, the pink color shape here, the weight of here is W, is equal to, let's say W. So we have here W equal to FB. FB here is the floating bodies. Okay, for floating bodies only, weight equal to FB. Okay, weight equal to FB. Okay, FB is equal to, or so FB equal to W, we can also write F rho G V. Which V? VD. The volume displaced. Which one is the volume displaced? Only the volume here. Okay, only the volume here. Not included the entire volume of the physical object ni lah. Okay, not included. Not include. Okay, volume only. Okay, only this volume only, which is VD lah. Okay, VD. Okay, I will go for an example later. Okay, right. So here, rho here is the fluid density. The fluid density. V sub is volume of liquid displaced. In this case, is the half of the entire volume of the floating body. Okay, volume total, which is volume of the solid body, and then weight of the body. Okay, for floating bodies, you must remember that the weight of the entire body must equal to the buoyant force. So, if the weight of the entire body, we can write it as W equal to rho GV. Which V? The entire body. Okay, the entire body, V here, not VD but V. Okay, for volume force, here is rho fluid, is rho of the body, G is the same, V is different lah. D here is displaced, V here is the volume of the entire body. Okay. Okay, now so let's look at example. Okay, we have here a crane is used to lower weight into a sea, density of 1035 kg per meter cubic for an underwater construction project. Determine the tension in the rope of the crane to a rectangular cost 0.4 meter times 0.4 meters times 3 meter concrete block density when it is suspended, 1 in air, B, completely submerged, immersed in water. Okay, alright. So we have a crane. Okay, for example, we have here a crane. We have a crane. The crane is holding a block of concrete. Okay, a block of concrete. This is the block of concrete. This is the wire lah. So we have a wire here. We have a wire. We have wire. And we have concrete. Okay. So wire from the concrete. So the question is they want you to find the suspension. So for example, we have here Ft. So we have here weight from the concrete, and we have Ft from the wire. The wire is holding the concrete. So we must have force to hold the concrete from falling. Okay, so one, they want you to find the Ft, the tension in this the tension in this wire when suspended in air, and B, when you submerge in water. Okay. Okay. All right. So first of all, when you are facing this kind of problem, right? Draw a free body diagram. So let's draw a free body diagram. So here we have a block concrete. So what kind of forces is applied to the concrete? So we have one. We know that if we are solving the question 1, question A, we have only two forces. One forces from the Ft, which holding the block. Another forces is from the weight of the block itself, which is the weight. So we only have two forces here. So if you Ft minus weight, we got to 0. Why 0? Because you are suspending the weight in air. Suspending means that static, doesn't move. Okay, so Ft equal to W. So if you want to find Ft, we're solving A, we are solving A, Ft, and then we got equal to weight. So what is the weight? So W is equal to, we know that weight is equal to rho GV. Which V? Which rho? Which V? Now we are solving the in air, so the rho we are looking at is now the rho of the block itself. So what is the rho of the block? So the rho of the block is said here density, concrete block density 2300. Okay, so 2300. 2300. And then times G 9.81, and then times V. V, we already know that he said that 0.3 times 0.3 is the block. 3 times 0.4. If I'm not mistaken. Sorry. 0.4 times 3. Okay, sorry. 0.4 times 3. 0.4 times 0.4 times 3 meter. So if you calculate, so we got the answer is 10.8 kilonewton. 10.8 kilonewton. This is when it's suspended in air. So what happens if you submerge the block completely in water? Okay, so we have here water surface, and then we have wire, and then we have here wire is standing here, is holding the block in the water. So right now, since we are submerging the block in water, so what kind of forces is involved? So we have, from before we have Ft, and then we have weight, but since the block is in water, so we have the force from water, which is buoying force, Fb. So you have three types of forces. Okay, so three types of forces. Okay, so for example, you say that if the force is moving upward, is positive. Okay, so Ft, we're solving B minus W plus Fb equal to 0. Why 0? Because we are holding the block in water. Holding the block in water, so the mean is static, not moving. So we want to find Ft. So Ft equal to weight minus Fb. So we already know that the weight of the block is 10.8 kilonewton. We need to find the Fb. So what Fb? So we also know that Fb equals to rho GV. So which rho? Now we are solving Fb. So we are solving Fb. Rho is rho the water displaced, rho of fluid. So you now the concrete is submerged in the seawater. Okay, the rho of seawater is 0.25 kilogram over meter cubic. And then we have V. So which V? So the concrete is now completely submerged. Completely submerged means that the whole concrete is in water. So the volume right now is the same. The same is the volume of the concrete right now. So volume, we know that the volume of the concrete is 0.3 times 0.3 times, 0.4 times 0.4 times 0.3. 0.4 times 0.4 times 3 is the volume of the concrete. So yes. So the volume of the space is the same as the volume of concrete. So instead, just use this, substitute the value 1205, 9.81, and then we have the volume V. So volume V. So have the volume V, and then what is the answer? Yes, we look at the answer. the answer unit 4.8 kilonewton. 4.8 kilonewton. So we got 4.8 kilonewton. This is the Fb. So subtract 10.8 minus 4.8 kilonewton, and then we got 6.0 kilonewton. So the forces that needed to hold the concrete in water is lower than suspended in air. Okay, that is the example. Okay, so we get the example 1. Okay, now. Alright. Now we have another example. We have a cube on the side is made of bronze having a specific weight 86.9 kilonewton. Determine the magnitude and direction of the force required to hold the cube in equilibrium completely submerged in water, be mercury. Okay, so this example is the same as before. Okay, for example, we have a cube. So cube means that all the side is the same. Okay, for example 2. So we have a cube. 0.5, 0.5, 0.5 means that 0.5 in all sides. Okay, we have a cube, 0.5 in all sides. 0.5 meter. Okay, 0.5 meter in all sides. Okay, the cube have a specific weight. So phase peak weight is gamma. Gamma equal to rho g is 86.9 kilonewton. This is 6.9 kilonewton over meter cubic. Kilonewton over meter cubic. Okay, and then what else we have? Okay, determine the magnitude and duration of the force required to the cube equilibrium completely submerged. Okay, means that all the cube is in the whether water or the mercury. So for example, let's solve number 1 first. Okay, we have here in water. So water, what is density of water? So water is the water as we know is 1000. If the density of water is not given to you, you must expect the water is to be 1000 ppm over the cube. So first of all, what I said before, if you want to solve any problem involving any question, just draw the free body diagram first. So let's draw the free body diagram. So we have here a cube into D. So what kind of forces involved in this cube? So we know that completely submerged, and we are holding the cube. We are holding the cube to be completely submerged. So means that we have another external force. Okay, we have, for example, right now we only have weight from the force. Sorry, weight from the cube. Then if the cube is completely submerged in water, so we have the force from the water Fb, and then they said we are holding the cube. So we're holding means that, for example, we have another Ft. Okay, we are holding the cube, so we have another one forces that, let's say that the force that holding the cube is Ft in the upper direction. So using the same method said before, let's say the force that moving upward is positive. Okay, moving upward is positive. So let's solve it lah. Okay, so let's write the equation Ft plus Fb minus W equal to 0. Okay, and then we've got Ft. We are going to find the force on Ft, the force that we are holding the cube. Okay, so Ft equal to weight minus Fb. So if you write the equation, you got the answer. I will just go to the answer, through the answer. Okay, you can read it later. I will give this slide to you. Okay. Alright, so the same as before. So 9.63. So we get the answer is 9.63 here. So 9.63. So weight. So let's calculate the weight first. So weight. We'll calculate the weight. Which weight? Weight of the entire body lah. So weight is equal to rho GV. We already known before GV. This you need to solve it yourself. Okay, V here. So we have another one FB. So FB also equal to rho GV. But which rho? Rho here is rho of the cube. Just remember, FB is rho from the water. So we have here rho from the water. So this V here is volume of the cube. And this volume here is displaced volume. Since the entire volume is immersed in water, so the volume here is the same. Alright, so you need to solve this one, and then we got the answer 9.63 kilo. Okay, so we already known here FB rho here is 1000, G 9.81, and then V you need to calculate it 0.5 times 3 lah, power by 3. Okay, here is we have the volume of the cube already given to us. You need to find it from here, rho. You need to find it from here. Okay, from here. Okay, just divided the value by 9.81, and then we got the rho for the cube, and then you calculate it, and then we got the weight. Okay, okay, so what happened if what happened if we submerge it completely in mercury. So the step is the same. So the step is the same, but you might find that the force that required, we got the answer will be in minus. The answer will be in minus. Okay. When you get the answer in minus, it doesn't mean that you are getting a wrong answer. Okay. By saying that, okay, now we are, for example, we have here is the block. Now we submerge the block completely in mercury. Okay, mercury. So the same here, Ft. So the same here, weight, and we have another one forces, Fb. So we want to find Ft. So Ft, for example, we consider it positive if we're moving upward. So plus Lb minus weight go to 0. So the same here, Ft go to weight minus Fb. Okay, you will find that the Fb will be larger than the weight. Larger than the weight, and then you will got your answer in minus. And you get minus. Here you get the answer in minus 5.74. 5.74 kilonewton. Why you get answer in minus? Because you need to push the tube in order to submerge it in the mercury. Why? Because mercury density is larger than density of the tube itself. This kind of example, if the same is you have a water, and then you have a foam. The foam floating. If you put a foam on the surface of water, the foam will float on the surface of water. In order for you to submerge the foam, you need to push the foam in the water. The same concept is the same for this kind of problem. If you want to submerge something in mercury, you need to push, not to pull. Okay, so we got the answer minus 5.74. Okay, alright. So that we can answer. Now we will look at last one, stability of a floating body. So what is stability of floating bodies? Stability of floating bodies are defined by the meta center height Ymc and gravity center Ycg. Okay, if the Ymc is larger than Ycg, the body is stable. If Ymc is lower than Ycg, the body are not stable. Okay, for example here, I draw you another one. Okay, we have a water surface, and then we have a ship here. We have a ship. So what is Ymc? What is Ycg? Okay, right. So look at here. Okay, Ymc. Okay, first of all, Ycb. Ycb is center of the body. Ycg is center of the. Ycb is center of buoyancy. Ycb is center of gravity. Ymca is meta center. So we have 3. Okay, so since the ship is floating, okay, we have here. We will have Ycb around here. Cb. Cb means that center of buoyancy. Center of buoyancy. Okay. And then we have another one here. Center of gravity. Cg. Center of gravity. Another we have the upper one we have is MC. MC means that meta center. Meta center. Okay, meta center. So if we take the bottom of the ship as our reference level, here reference level. Okay, we got here. Maybe different color. So the distance from our reference level to the CB, we call it YCB. YCB. Okay, the distance from the YCB to the center of gravity to the reference level, we call it YCG. And the distance from the center, meta center to the reference level here, the lower the sheet, the tip of the lower sheet, we call YMC. Yeah, so we have YCB, YMC, and YCG. Okay, BM. Another one we have is BM. BM is the distance from the center of buoyancy to the YMC. Okay, so distance from here to here, distance from CB to MC, we call it BM. Okay. Okay, now we already done here our note. So if YMC here, YMC is larger than YCG, okay, is larger than YCG, and then it is stable. But if the YMC is lower than YCG, it's not stable. Now, how we calculate YMC and YCG? The YCG is very simple. You need just to divide it. You need to find the center. You need to find the center of the body. But YMC, you need to find it using here. Okay. The stability of floating bodies. This is the procedure of finding the stability of floating bodies. Okay. For one, you need to determine the shape of the area, the surface, compute the smallest moment I. Okay, and then compute the displaced volume VD, and then compute the BM, IVD, compute the YMC, YCB, plus PM. First, so first you need to find the YMC in order to determine whether the body is stable or not stable. Okay, so YMC can be written as YCB plus PM. YCB plus PM. So what is YCB? So YCB is equal to YCB center of body. So it's center of body. So center of body. So for example, you have a square like this. So the center of body. So the B we have here, from here is A. So the center of body of this cube is just B over 2. Here, so B over 2. And then if you have a triangle looking like this, and then the center of body is B over 3n. Okay, so for this kind of question, please look at the we have here center of body. Where is it? Okay, here. Yeah, we have here. So the center of body for a square like this is B over 2. If you want the center of body of a circle like here is R, and the center of body of the triangle is B over 3. Okay, B over 3 here, and then the center of body of the is 4R over 3 over 3 pi. Okay, and then we have another one. Alright, so you need to know what kind of shape that is involved, and then we need to know that how to find the center of body. Okay, so BM is equal to BM is equal to ISS over VD. So I or XX or IYY over VD, depends lah. VD. So ISS or IYY or YIZZ is the second moment. For this kind of problem, you need to find the smallest second moment. For example, we have here the second moment of a square is a b3 over 12. Okay. So for example, we have a square looking like this. We have a b, this is 2b. Yes, for example, we have here is b, and we have a. So we know that the second moment of a square is ab powered by 3 over 12. So if you are talking about the smallest second moment, which one should be small in order the value of the second moment to be small? A or B? It's A. A must, we choose A. Here is B, A powered by 3 over 12. It's the same second moment. Why we choose A powered by 3? Because we want this moment to be the smallest. If you are using B powered by 3, the moment we give will be bigger. Okay? Alright, I hope you understand. Okay, so and then so that's the equation that you need. And this VD. VD is the volume displaced. So for example, if the cube is here, B over 2. Yeah. This is submerged B over 2. B over 2, the half of the B, and then the volume should be, for example, we have here A, area A times A power by 2. Area will be A power by 2 times B over 2. Why not B? Because we only consider the volume submerged, not the whole volume. Alright, so for your homework, please answer the question given and submit your work by today before 10 PM. 10 PM, 10 malam. Alright, the question is here. It's about a cylinder wood block float in seawater, shown the figure. Okay, the diameter and height of the cylinder are 0.2 and 0.5 respectively. Okay, and if the 0.3 of the wood block is submerged, okay, the wood block is submerged is 0.3 under the surface of seawater, find the density of the block. You want to find the density of the block first, and the magnitude of the force required to hold the completely submerged in water. Okay, the force required to push the block completely submerged in water. So you find. Okay, I will show you later how to solve, but you need to solve it yourself. Okay, alright. Okay, alright. So thank you. That's all for today. Assalamualaikum warahmatullahi wabarakatuh.